In this video, we're going to look at the growth functions that we studied in this chapter and their behavior for different size data sets. We're going to look at this in three ways: numerically, graphically, and what I like to call practically. So in this first case, we have a table, and on the left-hand side of the table, we have n, which is the size of the data set, and it ranges 1, 10, 100, all the way up to 1,000,000. And then we have the values for the different growth functions at each n. The first growth function we have listed here is a constant function. So constant functions always take the same number of operations to execute, no matter how big the data set is. One thing to note about constant functions, the constant's not always 1. It may be 20, it may be 1,000, it may be 2,500. It really doesn't matter too much what the constant actually is, because when we talk about complexity functions, we're worried about the behavior for really large data sets. And whatever the constant is, it's always going to stay the same no matter how big the data set gets. So in comparison, it's going to be small. So constant time algorithms are really good. Unfortunately, there are only a small subset of problems that can be solved with a constant time function. The next function we have here is logarithmic. Logarithmic grows extremely slowly in relation to the size of the data set. So we can see that even when we get up to a data set that has 1,000,000 items, it'll only need to do 7 operations for a logarithmic function, which is really good. The next one is linear, and linear just scales at the same rate as the data set. The next one is called quadratic, which is just obviously the square of the size of the data set, and we see that here we're starting to get to really big numbers. This E, 1E12, means a 1 with 12 zeros after it. It's just a shorthand way of writing that. The next one we have is cubic, which is obviously really, really big. And then exponential, which is 2 raised to the size of the data set. It got so big here that I couldn't even calculate the numbers. So it's very, very large. And we see that it gets very large very fast. So even n equals 100 is the number of operations an exponential algorithm would need to do is 1 followed by 30 zeros. I don't even know what you would call that number. It's really big. So now we have a graph that's essentially showing the same information. On the x-axis here, we have the size of our data set, 1, 10, 20, all the way up to 100. And then these lines represent the growth of the different complexity classes that we looked at. You can't even see constant on this graph because it's so small. Logarithm just barely peaks out above the x-axis, and linear is also really low. So we see quadratic right here, and then cubic and exponential immediately skyrocket even for very small values of n. So this is n equals 10 here. And we see that exponential grows even faster than cubic. If we extended this graph out to higher numbers, we would see exponential gets much worse than cubic much, much faster. So we see these really huge numbers, but then we also think, well, computers are really fast, so maybe they're working really fast and these big numbers aren't anything to worry about. And it turns out that a standard modern desktop computer can perform 1,000,000 operations in about 166 microseconds, which is not that long. And by a current desktop computer, I mean a computer with a 3 gigahertz processor that can do 2 operations per cycle, which is fairly common. So that's not that bad. But when we look over here and we see the behavior of a quadratic algorithm for the same size data set, we see that that takes 1 e to the 12th operations to perform that algorithm, which is this very large number right here. And modern computers can execute that in slightly under 3 minutes. So in some cases that may be acceptable, and in some it may not, depending on how fast you need to get back to your user. So next we have the cubic function on the same size data set. That would take 1 e to the 18 operations, and that would run just over 5 years, which in general is not an acceptable outcome. And then finally, for the exponential, even for data sets with only 100 items, it would take slightly over 5 trillion years to complete. In general, modern computers can only run exponential algorithms for about n equals 30.